Good morning. Hello, everyone. Thank you so much for coming this morning. Thanks for taking your time out today. Welcome to Tiger Talks for October. I am Donna Buss, and I'm with the Science Outreach Center here at Clemson. Today, we are so excited to welcome Dr. Naveen Vetcha from NASA. Yes, the NASA. This is our guest today. So he is the team lead of Aerosciences of the Aerosciences team in Huntsville, and he's going to be talking about his career journey. So remember to add any questions that you might have into that Q&A option that's at the bottom of your screen. And I'm going to turn it over to Dr. Vetcha. Take it away.
Hey, good morning, everyone. Nice to be here. And as Don mentioned, my name is Naveen Vetcha. I'm going to talk about my career journey from India to NASA as a contractor. I'm with the M&M Space Exploration Division. So that gets started. I grew up in India in 90s in a small town, and there is no way I could have
Okay, it looks like we have a frozen screen. Hang on, guys. Hang in there. He's connecting back.
Hey, sorry.
No worries. You're back.
Yeah, let me share again. Yeah, so during 90s when I grew up in India, and there was no internet or phone or things like that. So in the summer holidays, we used to go to my grandparents who lived in villages, and we used to sleep outside because there is no electricity and summers are very hot. And my grandparents used to tell stories about constellations, and we used to see dark skies with all the stars and constellations, and that kind of inspired me to get into STEM field. Astronomy, you can pursue it as a degree, but the opportunities are small. So that's why engineering or medicine is this is the path you could choose to contribute to these fields. So with that, I did my undergrad and masters in India, and moved to US to do my masters and PhD in mechanical engineering from University of California, Los Angeles. And then when here is a quick picture of various projects or programs I got to support in my career journey. On the top left, what you are seeing is something called nuclear fusion reactor. So you probably heard about nuclear fission reactors. Those are the reactors that produce energy that we use along with coal and gas and wind and hydraulic and all those power sources. Nuclear is also another option, but we want to use something called nuclear fusion concept. This is the physics behind how stars, the energy is produced inside a star like our sun. So we are trying to create an artificial star on Earth. So go look it up, learn about nuclear fusion. Just to give you an idea how big this reactor is, here is a person, 6 foot tall person to scale. And in order to understand this reactor and the physics behind what is happening here, you need to know, fluid mechanics, thermodynamics, heat transfer, some plasma physics, and a lot of mathematics. So that's what I was doing. You trying to understand how to extract heat from this nuclear fusion reactor so that we can turn a turbine and produce a power. And when I graduated, I moved to a small company here in Huntsville, Alabama. And what we were doing is probably you all have a computer or mm, a cell phone, and all of them there is something called chips. And what those are just a silicon wafer on which we kind of introduce some semiconductor materials to build circuits. And in order to do that, we do it in a small reactor. We take a round silicon wafer and we pump gas that contains semiconducting material so that it can be, spilled in a particular pattern. But before you do all that, you need to simulate that process on a computer to make sure it works properly before you go put millions of billions of dollars in building a facility to mine these chips. So that's what I was doing. Again, using a lot of physics and mathematics to understand that. And after working on that for about 3 years, I got the opportunity to work on something called James Webb Space Telescope. This is the biggest telescope that humanity has put in space, and I was the lead analyst for something called the Sun Shields. I'll talk a little bit more about that, but this is a unique opportunity for me, and I still can't believe I got to work on this. And when we finished that, I got to work on a big rocket that NASA is using to send humans back to the moon, and especially there are engines at the bottom of that rocket. Again, I'm going to talk a little bit more about that. So there are four engines at the bottom that use liquid oxygen and liquid hydrogen as a oxidizer and fuel for these engines. So I got to use mathematics to understand the performance of these engines. And once I finished about 30 or so tests and supported 30 or so tests of those engines, I got to work on a cool technology, like new technology. If with NASA's vision to have long-term human presence on the moon, we need to use material that is out there on the moon to build habitats, to build berms, to build landing pads, all that. So in order to do that, we need to develop new technologies to excavate, like dig up stuff from the moon's soil and use it, process it, so that we can use it in multiple purposes. Especially on the south polar region of the moon, there are something called permanently shadow regions. So these are the big craters where sunlight never entered. So there is ice embedded at the bottom of these craters in the soil. So we need to be able to dig that up and process it so that we can turn ice into water, and we can use water for many different purposes, just like on Earth, right? So I worked on that for about 4 years, and we developed some robots to test these concepts, and we are further developing those that technology by testing it in a big vacuum chamber and all that. But then I got to um, work on something called aerosciences, all related to rockets. When rocket launches, what happens on the body of the rocket? What are the forces on the body of the rockets? We need to understand that before we launch a rocket. What is the heat distribution on the entire rocket? What happens if the rocket blows up on the on the launch pad or while it is going up? We need to understand what is the blast wave that is comes out of that rocket, that is failure rocket. What is it going to do to the surrounding buildings and all that? So that's the purpose of that. All right, so with that, I'll talk a little bit about James Webb Space Telescope. So James Webb Space Telescope is located, we launched it back in 2022, and it's located about 1.5 million miles from Earth in something called a Lagrange point, which is a stable point for Earth and Sun and Earth gravitational field. It is a stable point where these gravitational forces from Sun and Earth match, so that that point always orbits the Sun with Earth. So the telescope, we can always see the telescope. And there is also another reason why we put this telescope so far away. That is to look at the universe in infrared part of the spectrum. What you are seeing here is something called electromagnetic spectrum, and here is visible light. This is the light that we can see, humans. But James Webb Space Telescope is going to look at the universe in something called infrared part of the spectrum. Why infrared? Because infrared tells us a little bit more information than just visible light. For example, on the left, what you are seeing is meerkats and a freshwater crocodile. When you look at them first time with visible eyes, you can figure out some things. You can tell about their color, structure, facial features, and body pattern. Any patterns on their body and all that, right? That's good. But when you put on your infrared glasses and look at them, you get a little bit more information. Okay, the bodies of the tummies of meerkats are glowing. That is telling us they have higher metabolism. Um, but you won't be able to tell that with visible light when you look at with naked eye, right? Because the fur covers their bodies. Even if there is no fur, you won't be able to tell the difference which is cold, which part of the body is hot. But with infrared, you can tell. Same with the freshwater crocodile. You see the difference between the color of the ground on which it is resting and its body. That's because maybe this freshwater crocodile was just swimming in a nearby hot pool of water, and it came up and resting, and the body temperature is kind of started to cool down. So that's a little bit more information you get from infrared. So big view, the telescope has two sides. One is the side where the big mirror, about 22 feet in diameter, is located, and its science instruments are also in the back. Lot of cameras and spectrographs. And on the bottom, you have all the antennas and solar power arrays and trackers and any communication devices. And the telescope is always looking away from sun and earth because, as I said, we are looking for the heat signature of distant objects. So if I ask you to go find fireflies in a big field, you want that field to be as dark as possible to be able to see the fireflies. You don't want to use floodlights or a big flashlight to look for fireflies. So this is what is exactly this telescope is doing, and the sun shield is blocking all the light and heat that is coming from the sun and earth. So that's why a telescope is always pointing. If this is the sun and earth, it's always pointing away from the sun and earth. um, this is about the size of a tennis court, the sun shield. There are five of them, and this is how we used to test them in the clean room here, where we used to deploy it in a big clean room and use the lasers to study the shape. Why we study the shape? Because we are developing mathematical models to predict the shape of this big sun shield in space, but we want to make sure this mathematical model is accurate. One way to do it is to deploy it in Earth and see what mathematical model is telling and compare it. And if it is not comparing it well, then we need to update the model. So that's what we did. So once the mathematical model is predicting the shape on Earth accurately, we have confidence in this model to predict the shape in space. So that's what we did for all the five layers. And this is the only picture they allowed us to take with our entire team in front of the sun shield. And as you can see, there are like three people standing there, and that's where I am. And this is how we used to ship all these layers from Huntsville to Los Angeles. Los Angeles is where this entire telescope is being integrated, and they used to ship it like within 48 hours. These truck drivers did an amazing job. Some science goals of this telescope: we want to understand the early galaxies, first galaxies that formed after Big Bang, first stars that formed after Big Bang. We want to understand what happens when the galaxies interact with each other. They say that there are new stars that form, new black holes that form when galaxies interact with each other. We also want to understand how stars uh, are born, evolve, and die. We also want to understand exoplanets, the planets that are far away from our solar system. These are the planets that are orbiting other stars. We want to understand their atmosphere and all that. We also want to understand a little bit more on the far planets in our solar system, that is Mars, Jupiter, Saturn, Uranus, Neptune, and all that, and some Kuiper belt objects. All right, so that's one cool project I got to work on. The another one is this one, the Artemis program. This is the program where we want to send humans back to the moon for long periods of time to stay there. And NASA wants to do it in particular steps. First, like develop launch vehicles like rockets and test them and understand them, and then send small robots, work with other companies, and send small rovers to navigate the land, understand the land, and all that. Everything will be at the South Pole. And long term, we want humans to be able to stay there for months. So building habitats and communication technology and the suits that they can wear to go outside, all that is important. So all that needs to be developed before we can confidently send humans to the moon, back to the moon to stay long term. And the first one is like the rocket. We need to have a reliable rocket to send them that far safely and bring them back. So that's The rocket space launch system is the rocket that NASA has been developing, working with commercial partners. Here is a kind of exploded view of the rocket. All this part, the biggest part on the bottom, is called core stage, and it has four liquid engines at the bottom and two solid rocket boosters on the sides. And all this will be gone within 8 minutes after launch. And this rocket, these tanks carry liquid hydrogen and liquid oxygen because that's what is being used by these engines at the bottom. And the first launch of this rocket happened in 2022, and it all went fine, and we learned a lot from this mission where we just sent rocket to the moon and brought it back um, to just test everything works fine before we put humans on the rocket. So the next one is coming up hopefully in February 2026. So look, watch out for this news and all that. So these are the four astronauts that will be launched on Artemis 2 from Kennedy Space Center. They will go to the moon, orbit it, and come back and all that. They are not going to land on the moon. Just to again, in the baby steps. First, test the rocket. Next, make sure humans can be sent to the moon, and we can bring them back safely. And then the next step is to be able to land on the moon. So for those rocket engines that I mentioned, as I said, they're at the bottom. There are four of them. Each one produces about 470,000 pounds of thrust. And before we put them on the rocket, we have to make sure they can work. They work as expected. So we test them in big test site like this, test facility like this. This is at NASA facility in Mississippi. Stennis Space Center. You can tell the size of this by looking at these trucks here, the small, how small they are. And the rocket engine itself is sitting here. And that's why the exhaust is coming from bottom here. Can you guess what this is coming out as an exhaust? This rocket is using liquid oxygen and liquid hydrogen as the oxidizer and fuel. When you mix oxygen and hydrogen, you get water. So the exhaust that is coming out of this engine is water particles. And that's why you see this big rainbow, because it's like a rain. If you are actually standing a few yards away safely, the safe distance, you can feel the rain for these tests. So we used to test these often, and I supported about 30 of those tests, and we were confident that these rocket engines performed well. So just summing it all up, I have been supporting NASA in various capacities for the last 9.5 years. If you ask me at your age, between 8 to 12 years or in the middle school, if you told me I would be working or I would be supporting NASA, there was no way I could have believed it, because there is no path. I'm back in India, so it's a far away. I didn't even hear about NASA at the time. So what I'm coming to is, dream what you want to do, because you may not know the path now, but you will make the path as you grow, as you progress in your career. I got to meet a lot of cool astronauts and got to work on some cool technologies and all that. So some lessons learned, as I said, know that your path to your dream job or field may not be straight. If you immediately after graduation, if you can't get into, let's say in my case, aerospace, if you can't get into aerospace, find a tangential field where you can apply those skills. In that way, you are having all those skills, and when the opportunity comes, you can just jump on it and use all your skills and experience. For your age, internship opportunities is not kind of appropriate for your age, but look for mentors in your school or in your nearby university, and work on team projects, some cool technology projects. And there are a lot of professional societies. You may not have heard about those, like American Institute of Aeronautics and Astronautics, IEEE, ASME. These are all professional societies into which you can join for free. You are all students. even including some teachers that are on this call. You can all join for free and uh, invite professionals to speak to your class or ask them to come and help you with the projects. So, and then for students, find a mentor. I still have a mentor. I'm 10 years into NASA, but I still need a mentor when I have questions or when I, hit a brick wall. And then whenever you have an opportunity, stop and celebrate your achievements, this because this is what you remember. Those are the milestones you remember. And don't hesitate to ask questions and ask for help, because again, even after coming to us, path to NASA was not visible to me. But all I did is like network and ask them questions like, hey, how can I improve my skill set to so that I can get into NASA? And if I see an opportunity, I know somebody in LinkedIn, and ask them, hey, can you put us in touch with the hiring manager so that I can get an interview opportunity. The worst case is what you get is no, I'm sorry, but that's fine. Keep asking until keep knocking the door until somebody opens it, and you take that opportunity, and then you will excel when you have that passion. With that, I'll open up for questions.
Hey, thank you so much. All right, so one of the first things you talked about was your education. And so one of the questions came back is, did you need, do you need all of those masters to be in aerospace engineering? So,
No, you don't. Bachelor's is enough. For some, we actually, I mean, I'm a team lead now. I have about 25 people on my team, and there are some people called SMEs, subject matter experts. So these are far smarter than me, but some of them have only bachelor's degree. They learned a lot on the job,
mhm.
and even a PhD person, even a professor will come to that person and ask questions. And remember, there are a lot of technicians that we need to build these rockets. So whether they are plumbers, electricians, all that. So any degree that welders, like we need very good welders to be able to work on space hardware. So pursue, look into those opportunities too. Yeah.
And one that kind of builds off that about the rocket from this is a little bit more towards the beginning too. How many of the nuclear fission tanks do you need for the rocket?
Oh, we are not using nuclear fission yet to
Okay,
power the rockets.
okay.
It's a future concept. Yeah.
Ah, um, how do you process the moon and what does the robot do with that sample? You were talking about that much early on too.
Yeah. So how do we sample? What is that? Sorry.
How do you process the moon? I think you were talking
So
about that
the
much.
process. So what we do is like there is we call it regolith, which is just a moon soil on the moon. We need to be able to dig that up. There are some challenges with that because first the temperatures are so low. It's like minus 430-degree Fahrenheit. Our equipment, our digging equipment that you see in day-to-day life, that won't function at those temperatures. So we need to develop that. Yeah. And then it's vacuum, so there is no air that is cooling this equipment. Just like here, there is air and there is fluid that can cool, and there is radiation. Materials can't withstand radiation for a long time. So after developing the technology, when you dig that up, you need to be able to separate the ice from the soil. So that's the processing part. Even with the soil, you can use it to build bricks, using which you can build habitats, or you can also pile it up and create berms and landing pads and all that. But to do that, you need to process, like you need to separate pebbles from like a fine sand and all that. So that's the processing part. um, and coming to the back to the ice, once you get ice, you need to be able to convert that into water and use electrolysis to convert that into hydrogen and oxygen so that you can use it as a rocket fuel also, right? So that's all the processing part.
Okay, so here's a real general question. How many people have landed on the moon, and did you work on any of those?
No, that I'm not that old. I think there are about 20 astronauts or so that landed on the moon back in the Apollo time frame, 1969 to 1975. Yeah, I didn't get to work on any of those.
He's too young for that. All right. Do you name the rockets?
Yeah. Overall mission, it's Artemis 1 and Artemis 2. Instead of the rockets, the spacecraft in which we put astronauts, they astronauts name it. Uh, like I forgot what they named the Artemis 2. These four astronauts that are going to be launched on that, they decide the name of the spacecraft.
Keep those questions coming. Let's see. What is your favorite thing to do in NASA? At NASA.
Oh, wow.
These are what they want to know is what do you
That's
like to do?
a very broad question, but
Yes.
working with people, that's what I enjoy right now because I'm in the team lead position. Work taking an idea and making it a reality, like the ice mining uh, concept that I did back in 2019. We were just sitting in the room and brainstorming what can we do so that we can advance this technology. And from just that paper idea and a meeting to be able to demonstrate that in June 2024, where we had like 6 robots and trying to lift them using a crane to simulate the gravitational conditions on the moon, which is 1/6 the gravity, and then let the robot dig from a concrete pad. It's like working with people and seeing that idea from on-page idea to the actual reality is what kind of gives me goosebumps sometimes when you think about it. Yeah.
How many months or years does it take for the moon to orbit fully?
Fully. I mean, it's every month. That's why moon and month, month, month and moon. A month came from the word moon. It's about 28 days.
Okay, there you
That's
go.
why we see the phases.
Why do you know why they picked the name Artemis? Artemis 2? Do you know why they
Yes, yeah, yeah. So back to 1960s, the first mission to send humans to the moon is called Apollo. In Greek mythology, Apollo is one of the gods, and Apollo's sister is Artemis. So back in 2019, 20, not 2019, 2018 or 2019, that's when NASA administration picked Artemis to be inclusive of everyone, to dedicate this program to the entire humanity. Because this will be the first time a female is going that far into space. The goal is to have first female to land on the moon through this program. So Artemis is a very appropriate name. All the Apollo astronauts that landed on the moon are male.
do you have a favorite rocket?
Saturn V, because that's what took us to the moon and made what we considered impossible a possibility.
Um, do you have a suggestion that they used because they thought it had, I think what they're trying to say is, did you ever have a suggestion that they actually used because they thought your idea was good?
Yeah, going back to the what we call ISRU, in situ resource utilization, that means using the material that's up on the moon. Um, how do we simulate gravitational conditions on the moon? It's 1/6 gravity, and combining everything, like creating a vacuum that big in the space and creating a soil that has the same properties as the moon soil, and also simulating moon's gravity. All of these can't be done without billions of dollars. So what we did is, okay, what if we just use a crane to apply a counterweight? If the robot weighs, let's say, 600 kilograms, let's apply a 500 kilogram counterweight so it only feels 100 kilograms. So it's a simple, few $1,000 technique to simulate gravitational conditions on the moon.
Beautiful. All right, I think we've come to the end of our questions. I want to thank everyone so much for coming, especially you, Dr. Vetcha. Thank you so much. I do want to let you know that next month, November the 20th at 9:30 a.m., we'll have our next speaker, Jonathan Wyndham. He'll be talking about plant breeding and biotechnology. So again, thank you, Dr. Vetcha. Thanks
Thank you.
everybody else for coming, and I hope you have a great rest of your week, and we'll see you next time, hopefully. Bye,
Thank you.
everybody. Thank you again, Dr. Vetcha.
Yeah, all right. Take care. Bye.
Bye now.
Mhm.